All right, kids, we'll get started here today. Tangent line approximations is going to be our section for 4.8 that we're going to discuss today. A couple things I'm going to tell you here prior to going through this here is make sure that you're checking online this week to see where everything's at. All the stuff you'll have will be definitely on Mr. Parsons' math page, so everything that you'll do this week while I'm gone will be there. And if you have questions, we'll chat through Google Meet, probably Tuesday a little bit at the beginning of class, and Wednesday through Google Meet at the beginning of class, and I'll chime in with some about it. But guys, we're in the last section of Calc, Chapter 4, and tangent line approximations is what we're dealing with. We've spent a lot of time talking about tangent lines, and this is kind of a shortcut way to help us get approximations of functions. But it also is a new formula to help us get tangent lines for any specific point given a function and a known derivative. So what we're trying to understand today is this. We're going to have to be able to understand how to use linear approximation to estimate values of a given function. So right here, a little paragraph. Excuse me. It says, in our study of the derivative, we have frequently referred to the statement tangent line to the curve. Okay, this has been something that's been focal for us this year. And we've spent a lot of time writing tangent lines to points on a curve. What makes a tangent line so important mathematically is that it provides a useful representation of the curve itself. In other words, it tells us how quickly something is changing. We've talked about instantaneous rates of change. But it also provides a representation of the curve itself if we stay close enough to the point of tangency. Okay? So guys, what we're going to be able to do is we're going to be able to evaluate some functions on a curve, knowing what our tangent line value is, as long as we stay fairly close to your point of tangency. So we use this concept to help us estimate the value of a function by using only that line of tangency. So again, the idea is we're still talking about tangent lines, and the idea that approximations are just that. We're going to get an idea of what some values are based on our line of tangency instead of using the function. But understand, tangent line approximation means we're getting an estimate close to a value that we've known for our line of tangency. So key term today that you're going to hear is called locally linear. Locally linear is a good way to think of a differentiable function, is that they are locally linear. That is, a function that is differentiable at point A closely resembles its own tangent line very close to that point. And I'll show you some drawings here in a little bit, but what's written right up here is going to tie in really well with this stuff down here, all right? So linear approximation has this formula, okay? Using linearization, or sometimes I like to write TLA for tangent line approximation, following is true. If f is differentiable at x equal a, so in other words, some value a is some number, okay? If f is a differentiable function at x equal a, then the equation of the tangent line is the following, okay? The tangent line is defined as f of x, and that tangent line is approximately the following formula. It's given f of a, where a is some number, plus f prime of a, so derivatives are going to come into play again, times the quantity x minus a. Keep in mind, a is some number, all right? That formula is going to define the linearization of f and a, okay? Basically, this formula right here, this will give you the tangent line equation at your given point A, and then we're going to use that to estimate some values around a using the line of tangency rather than the function. So, this is going to approximate f of x, which we say is approximately our line, okay? And it is the standard linear approximation of f and a. The point x equal a is the center of the approximation. So we always need to know our a value. We must always know what a is. And it's going to be your point of tangency is where a is going to lie, okay? So bottom line here, I know there's a lot of wordiness in there, and it's probably kind of confusing right now, but visually, what does this mean? Well, let me show you real quickly. All right, bottom line for labeling. A couple of things that I'm going to put down here. I'm going to kind of divide this up. This will start working. And here's what's kind of happening, okay? You might have some graph that looks like this. So I'm just gonna sketch a coordinate plane here. Okay, you might have some graph that kind of looks like this. I have no idea what your graph is gonna look like, okay? Now, the thing that we're gonna start running into is situations like this. You might know that this here, my friends, okay, this is gonna be the value A right here. Okay, this is like saying on the x-axis, we know this A value. It is some number, okay? And to that point A up there, to that point A, there's gonna be a line of tangency. Now, we've talked about finding lines of tangency before, but there's a line of tangency that goes through here. That's kind of a big line, so let me narrow that down. And I'll make that a little bit more. That's too big still. Okay, let me fix that real quickly. I'd say that's probably a better tangent line right there. Now guys, here's what we're kind of talking about today with this line of tangency. This line of tangency's formula is going to take on the following. This line is going to be defined by f of x equal f of a, okay, plus f prime of a times the quantity x minus a. So here's the situation, kids. When we start looking at stuff today, we're going to say, well, we're concerned about x values around a. So there might be a point like maybe right here, kind of close to a. Instead of evaluating that point right there, we jump up to our tangent line and say, well, what if I use this value right up here? Okay, what you're going to find out is that these two values right here, they're pretty close. They're locally in the same spot. We say that this is the local linearization of a curve given that tangent point at A. All right, so some things that are going to happen are this. Sometimes, as in this line, where this point lies, and where the value for the tangent point lies for this particular x value, near A, we would say that value is going to be an overestimate because the tangent line is completely above that. So things you're going to see in this section are this. If I have a tangent line that's to a graph where it's increasing, my graph is increasing everywhere, and concave down, my line of tangency will always lie above. So the only point it's going to share is that line of tangency. That's where your point A is. Okay? And if I have a point of tangency at A, then my estimates on the blue line are completely above the curve down here. I would say that the points on this tangent line are going to be an overestimate. And again, we'll look at some examples where we see this, but that's definitely going to be an overestimate. Same game with the graph that's decreasing. As I read this from left to right, my graph is decreasing. If this was my line of tangency right here, well, the only point that's shared would be this point A, right here. We're going to use that following formula to get an equation for the line of tangency. If I said this is the particular x value I'm concerned about, one right above the other, well, in this case right here, my tangent line approximation and my actual value right here, that tangent line approximation again would be an that would be an overestimate. So kids, these first two graphs, both of these are concave down. Both are concave down. When graphs are concave down, a tangent line approximation will definitely be an overestimate. Now the two graphs below here, if I draw a line of tangency down here, or a line of tangency, say maybe right here at A, doesn't matter where I put it, those two tangent lines are going to lie below the actual graph. So any graph that is going to be concave up, as these two are, any graph that is concave up, where these two are, a tangent line approximation, that's the actual point, and this here is the tangent line approximation directly below it for a particular value of x. In that case right there, these are going to be an underestimate. Well, let's see. Estimate. Hope I spelled that correctly. And I'm going to say it's for this particular graph and for this one here. Okay? So far, kids, tangent lines, when the graph is concave down, like the top two, approximations on the blue line will be an overestimate. Okay? And when a graph is concave up, like we are in the bottom two graphs, then you're going to have some kind of an underestimate. All right? So with all that right there, I know it's probably a little confusing to this point. start looking at some examples right here on page 2. When you're going through notes, pace yourself. If you need to pause the notes, I don't have an audience in here on Sunday night right now, but make sure you pause, get down what you need, and then think of questions. If you think of questions, write them down in your notes, and I'll chime in with you tomorrow on Google Meet. All right? All right, second page. Here we go. Okay. Guys, example number 1 states the following. It says, suppose the following. It says, given a function f of x is equal to x squared. It says, estimate the value of 2.1 using local linearization. So we're estimating. Now, guys, I could, if I wanted to, take 2.1 and plug it right in here. Okay, in fact, if I would just plug it in, f of 2.1, my friends, actually is the same as 2.21 squared, or 2.1 squared, I'm sorry. Is the same as 2.1 squared, which I know is 4.41, okay? So the actual value on this is 4.41. Now the idea here is use your local linearization right here to come up with an approximation of that using linearization where our a value is 2. We are saying use that tangent line approximation around 2 such that we can get an idea of what f of 2.1 would be without having to plug it in. So here we go. It says, is this an overestimate or an underestimate approximation and why? Well, let's do the first part right there. You guys know the function f of x equals x squared is simply a parabola, a U-shape. That, my friends, is concave up. And on a previous page, we said anything that's concave up, our tangent line approximation will be an underestimate. Okay, it will be an underestimate. Okay? So how do we come up with this idea of the tangent line using linearization? Okay? Well, here's our formula. We start this out as f of x is approximately f of a. And in this case, kids, a is, again, 2 plus f prime of a times x minus a. Okay, so watch what happens here. Again, we know that when we plug 2.1 into the actual function, we're going to get 4.41 out. Okay? Now again, understand the concept. Don't ask why we're going to go ahead and do it this way. We're not saying that we're doing it this way all the time. We're just saying that this is another way to think about how to get approximations of values on curves without actually having to put them in a function. Once you know a tangent line at a point, we can get some pretty good approximations near that a value. So here it is. First thing we would need to know is this. We know f of x is equal to x squared. We would also need to understand that f prime of x by power rule is 2x. So what we start doing is we say, okay, let's evaluate this at f of 2. Our tangent line approximation becomes the following. It becomes f of 2, which is the same as plugging into x squared. So 2 squared, my friends, for f of 2 would be 4. Okay? Plus. Okay? Next thing we need to do is evaluate f prime of 2 right here. Well, guys, we know the derivative is 2x, so if I plug 2 in for x right there, 2 times 2 is 4. And then we have this quantity, x minus that a value of 2. So a tangent line approximation for us, friends, is the following. It comes 4 plus 4x minus 8. Okay? 4x plus 4x minus 8 after I distribute, which would simplify to the following. 4x minus 4. So our tangent line approximation in example 1 is the following. F of x is approximately 4x minus 4. Now the unique thing about this is the following. Okay? I'm going to go into decimals and show you what this looks like visually. But what we want to do is use this tangent line approximation to approximate f of 2.1. Again, keep in mind, we plugged it into x squared. We know it's going to be 4.41. But just to make sure that you understand what's really going on here, let's take a look at this. So originally, we had the following function, x squared. So let me get that in there. And we said we're concerned about the x value of 2.
Guys, when I plug x squared to be 2 in there, when I let that a value be 2 or x be 2, I get an output of 4. So this is like saying we want a tangent line at the point 2 comma 4. Okay? All right. Don't know why that's not showing up. Why is that not showing? Oh, because I'm not at home. There we go. 2 comma 4 right there. Okay? Now, check out your tangent line approximation that we came up with. 4x minus 4. You'll notice right here that what we have is a tangent line approximation. Now, the thing that we're kind of worried about, guys, is this. 2 would be right here for an x value. 2.1 is pretty darn close to that. We're concerned about this area right in here. If you look at this tangent line from about here all the way up to here, boy, those points are really close to each other. And we can kind of use this part of the tangent line right here, say from about this area right here up to this area, to evaluate what the green values would actually be. It doesn't get to about here until we start becoming way off. So if I say we can find values around A, we're saying, okay, this is the point we started with. We can find some approximations of the green graph on this black line fairly close to that point right there. Now, again, when you get further away, then you've got quite a gap. But right around from here to here, those lines pretty much overlap each other or very close to each other for a little bit. And that's kind of the area we're talking about right here with tangent line approximations. So, back to this example right here, guys. If I look at f of 2.1, this becomes approximately 4 times 2.1 minus 4, which is the same as 8.4. That's what 4 times 2.1 is, minus 4. We get an approximation of 4.4. Kids, relative to what we knew we were going to get, 4.41, the estimate at 2.1 was 4.4. We are very close. Okay? Now the question goes on to ask, well, let's do f of 2.5. Okay? If I would do the actual rate here, in our function x squared, 2.5 squared, I know is 6.25. Okay? 6.25. But by tangent line approximation, if I use the 4x minus 4 to get an approximation, f of 2.5 would be about 4 times 2.5 minus 4, which becomes the following. It becomes 10 minus 4, good buddy, which is 6. All right, now keep in mind, 6 is pretty close to 6.25, but the question says, well, what's happening to the accuracy as we get further and further away from the a value of 2? Repeat this with 2.5. What is happening to the accuracy? The accuracy, we were 1/100th off at 2.1. At 2.5, we're 25/100ths off. So the idea here is the further I get away from A was 2. The first approximation was at 2.1, pretty close to 2. The second approximation was a little farther away from 2 at 2.5. The idea here is this. Once you get further and further away from A, your accuracy is becoming less accurate. Okay? So when I say right here, what's happening? Well, I would say, probably write this down. Probably say, oops, hang on a second. Technical difficulties, never fails. Okay, I would just say, as you get further away from X, I'm going to squeeze it down in here, kids. As we get further away from A, that A value that was given, okay, approximations are, or estimates are, less accurate. Squeeze it in here. There's an E in there. Okay, so the further we get away from that A value, we're going to say estimates are going to be less accurate there. All right? There we go. All right, let's try another one here, kids. So same idea. We're going to come up with a tangent line approximation, different function. Okay? F of x is equal to the square root of x. Find the linear approximation at the point A equal to 25. So we know we're dealing with A equal 25. It says using this linear approximation to estimate the value of 24.8, F of 24.8. Is this an underestimate or an overestimate? And why? And we'll talk about the why. It's either concave up or concave down. Again, if it's concave up, it's an underestimate. If it's concave down, it's an overestimate. So the things we need to know here are the following. First of all, we need to evaluate f of 25. Okay? We need to evaluate f of 25. Kids, understand this. This is a function. I get square roots can be positive or negative. Since there's no sign out in front, assume positive. So f of 25 would equal the square root of 25. That's going to be 5. All right? Now we need to do f prime of 25. Well, kids, I don't even know what f prime is, right? But I know the function is the square root of x, which is like x to the 1/2 power. So the derivative of x to the 1/2 power, I'm going to write my derivative right up here. F prime of x would equal 1/2 of x to the negative 1/2 power times the derivative of what's inside, which is 1. I don't really like this negative exponent, so I'm going to move that to the bottom, so it's like 1 over 2 times x to the positive 1/2. And this is the same as 1 over 2 root x. Okay? So f prime of 25, my friends, would be 1 over 2 root 25. Let's see, the square root of 25 is 5, so that makes the denominator 10, numerator 1. Okay? So by tangent line approximation, here's our function again, f of x. For your curve will approximately be f of a, which in our case is f of 25, plus f prime of a, or in this case, f prime of 25, times x minus a, or in our case, x minus 25. Okay? Well, friends, f of 25 was 5. F prime of 25 was 1/10. And this is times the quantity x minus 25. So we'll go ahead and distribute here. I've got 5 plus 1/10 x. And then 1/10 of 25 would be minus 2.5. So in simplest form, here's our tangent line approximation. We have f of x is approximately 1/10 x. And then the 5 minus 2.5 part, this and this, those constants would combine to be a plus 2.5 on the end. Boom. Okay? Now, here's the deal. I could go into my calculator. Oh, shoot, I didn't want to do that. I could go into my calculator and be like, all right, what is the square root of 24.8? So let's just check it out. Again, 24.8, that's only 2/10 away from 25. So, in my calculator, let me pull this up here. If I go square root of 24.8, there we go. So if I go 24.8 and square root that, in actuality, we get about, we'll go nearest 10th on this, we get about, oh, where's the square root key? I think that's it, hope that's it. We get about 4.9799, it looks like, okay? 4.9799. I'm just going to jot that down. The actual is about 4 points. We said 4.9799. Okay. Now, if we go with our tangent line approximation over here, how close could I have gotten to that actual value of 4.9799 by just plugging into our tangent line approximation? Or an x value, 24.8 near A, 25. We could have also done this. F of 24.8 will be about 1/10 of the x value we're concerned with, 24.8, my friends, plus 2.5. My friends, 1/10 of 24.8 is, move the decimal one to the left, 2.48, plus 2.5. My north of Highway 3 math skills would tell me that is 4.98. And kiddos, when you think about 4.98, that is very close to this, okay? Now, 4.98, a little bit of an overestimate. A little bit of an overestimate, and why? Well, let's take a look at the function. If I go in here and graph the square root of x, that's what we get. Your graph is concave down. Therefore, every tangent line up here is going to be an overestimate. Thing I love about this decimals here is you will know you've done your tangent line approximation correctly for that a value if your function hits that a value on the graph. So in this case, I'm worried about the x value of 25. I want my graph to be tangent at x equal 25. Our tangent line approximation was 1/10 x plus 2.5. Okay? If I zoom out on this, get to 25. If I click the two graphs right here, I hope they tell me where they intersect. I think they do. Maybe they won't. Let me change this real quickly. We can see this better. If I change this a little bit, my friends, they give you an intersecting point at 25.5. That is the right place. We have the right equation. Okay, again, the graph is concave down, therefore this must be an overestimate. Someone says, is this an overestimate or underestimate, and why? You're going to say, Parson, this is definitely an overestimate because the original function, square root of x in this case, is concave down. Okay, so let's just jot that down. This is going to be an overestimate, and this is proof right here, value-wise here and here. We just showed, going to be the same, but a little bit over, right? So it's an overestimate because the graph is concave down. Okay. So in a nutshell, we've got two really good examples about what tangent line approximation is, how we use it, and again, understand that we're trying to evaluate points on the original function near a certain value using a tangent line instead of the original function. Right? Okay, page 3, friends. So right here, same game right here. This one here is worded a little differently, but it's nothing that's tricky. Okay, could I punch in the cube root of 63? Absolutely I could. Okay, I could absolutely punch that in. All right. And in fact, if I punch that in, we get about 3.97. Okay. All right. So it says use linear approximation to f of x equals cube root of x and a equals 64 to estimate cube root of 63. Okay, so our a value is 64, and then they're going to use tangent line approximation to evaluate the cube root of 63. So friends, here we go. We know that f of x equal to the cube root of x. That's like saying x to the 1/3 power. Okay, so f prime of x, my friends, becomes the following. This becomes equal to, help me. It becomes equal to 1/3 x to the negative 2/3 by power rule. And I'm probably going to write this as 1 over 3x to the 2/3 like this. Okay, so we have our derivative. We have our original function f of x. We have our derivative f prime of x. So now we're concerned about an a value. And in this case, our a value is 64. So we need to know what is f of 64. Or in other words, what is the cube root of 64? Well, I'm not a genius at math, but I know that's 4. Okay? Then, we need to know f prime of 64. Well, here we go. This would become 1 over 3 times 64 to the 2/3 power. Okay? Let's think about this. This 64 to the 2/3. I know the cube root of 64 using this part right here. Cube root of 64 is 4. And then 4 squared using that 2 in the numerator. That'd be 16. So this is like 1 over 3 times 16, which is 1 over 48. So here we go. Our tangent line approximation. We end up with f of x is approximately, we want f of 64 first. In this case, that is 4 plus my f prime, or my slope, if you will. In this case, 1 over 48. Okay? And then this is times x minus 64. Right? So I'll simplify this quickly. So what we end up with here, kiddos, is the following. We end up with f of x is approximately 4 plus 1/48x minus 64 over 48, which I can tell you reduces to 4/3. Okay? Now I'm going to treat this 4 up here, this 4 over 1, I'm going to treat that as like 12 over 3, so I can combine with this. So 4 would be equivalent to 12 over 3 here on the left. 12 over 3 minus 4 over 3. That's going to be a positive 8 over 3 in the end. So this becomes 1/48 of x. And then, again, this 4 is like 12 over 3 minus 4 over 3. That would be 8/3 left. Here's our tangent line approximation. Now, use that to evaluate the cube root of 63. Well, no problem. We're trying to say, all right, we've got that tangent line approximation. Let's throw 63 in for x and see what the heck comes out. So this becomes 1 over 48 times 63 minus 8 over 3. Or I'm sorry, plus 8 over 3. All right, so let's see what we get here. If I go calculator here, the 1/48 of 63, that's like 63 divided by 48. Okay, that's 1.3125, so I'll write that down, 1.3125 plus 8/3, so 8/3, 8 divided by 3 is that value, 2.6 repeating. If I add in that first part, of 1.3125, check it out, guys, almost 3.98, 3.97, so on, okay? Cube roots at the right of the origin are going to be concave down, which would force this to be an overestimate, all right? But again, nothing different here. Understand what f of a is, understand what f prime of a is, understand the a value you're working with. Come up with your tangent line approximation. Once you have your tangent line approximation, plug your value into that. It'll give you a really good idea of what your value is on the original curve, okay? So the value we came up with here is about 3.98 again. All right, again, kind of the same thing. We're going to do number 4. Number 4 is going to go ahead and work a little bit with some trig functions. But I think that you're going to find out this is kind of the same thing. Okay? So my friends, it says find a linear approximation of f of x equals sine of x for x close to 0. So we're talking about everything around 0. So that means 0 is your a value in this example. Use this linear approximation to estimate the value of sine of 0.3. Now understand when we start talking trig functions, you're always going to use radians. You will always use radians from here on out if you see any trig functions. Question is this an overestimate or an underestimate? Well, let's do the actual right now, and then we'll tell. Okay, so if I go actual right here, I'm going to jump into my calculator. I'll make sure I'm in radians here. Hopefully it looks like I'm in degrees up here, so I'm going to switch that to radians. I'm going to type in 0.3, and then I'm going to go sine. Maybe. There it is. Sine of 0.3, we get about 0.2955. So the actual, I'm going to write this down, 0.2955 approximately. Okay? So actual is 0.2955. Okay, is this an overestimate or an underestimate? Well, let's find out. Okay? First thing we need to understand is we're talking about f of 0. Okay? F of 0 is going to equal the sine of 0, because the function is the sine of x, so we need to know the sine of 0. If you punched in sine of 0 in your calculator, it would be 0. Or if you looked on the unit circle on the web page, it would be 0. All right? Then, f prime of 0, we need to know that. Well, my friends, here's the situation. The derivative of sine is cosine, so we're concerned about the cosine of 0. If you would punch in the cosine of 0, you would get 1. So I know my f of a, and I know my f prime of a. So here comes our tangent line approximation for this, or your local linearization of it, or your linearization of it. Whatever you want to call it, you can call it, but I like tangent line approximation because it makes me sound smarter. So here we go. Tangent line approximation is the following. F of x will be approximately f of 0, which we already know is 0, plus f prime of 0, which we know is 1, times x minus 0. Now my friends, simplifying this is pretty darn easy. This just simply becomes f of x is approximately 1x. Okay? And as that's our tangent line approximation, we'll use that tangent line approximation now to estimate what the sine of 0.3 would have been. So we would be kind of looking for f of 0.3 by tangent line approximation. That's like 1 times 0.3. Ooh, we could be here a while for me to try and figure that out. But I got 0.3. And again, 0.3. And the actual 0.2955, guess what, my friends? This is an overestimate. And if it's an overestimate, this must mean that at that a value, at that particular a value, is this graph concave up or concave down? And it has to be concave down. Now, I want to show you what we were talking about right there. Okay? We had the function sine of x. I'm going to graph this. So in this graph right here, we end up with the sine of x. There is our graph of that. Now we're kind of concerned around our x value of 0. Right here is where we're concerned about. We came up with a tangent line approximation of y equals x. 1x, if you will. And so guys, I'm going to kind of zoom out on this a little bit, actually zoom in. What we're really concerned about is this graph basically from about -1 up to +1 right here. Talking about how this line kind of, you know, as we get closer and closer to 0 right here, this green line starting right about here just kind of overlaps this blue line up until about here is where it starts to break off. And when you start talking about this idea in calculus a lot, or especially in trig, this idea is pretty focal. Anytime you're dealing with values around 0, pretty darn close to 0, it's pretty much saying that the sine of x, so in other words, if this is like, I don't know, if I'm talking about an x value of 0.4 right here, the sine of 0.4 is really 0.4. Those values pretty much stay the same. If I just follow right through here, these values are pretty much all the same right here on the tangent line. But if I get on the blue graph and follow through, not exactly the same, but -0.25 is about the same as -0.247. -0.2 is about the same as -0.199. 0.21 is about the same as 0.208. So in this idea here, guys, in example 5, this idea is used pretty heavily a lot when we start talking about calculus or trig, where values of x are pretty darn close to 0. So let's just look at this last example. So again, it says, determine a linear approximation of sine of theta at theta equals 0. So here's the deal. We understand that a is our 0 value. We would need to understand what f of 0 is equal to. And we kind of did this in the previous example. This would become the sine of 0, all right? So when we talk about theta, theta is just like an x up here. They're just using angles now, calling those angles. So f of 0 would be the sine of 0, which is 0, okay? And, well, if we go f prime of 0 here, again, the derivative of the sine of theta would be the cosine of theta. So if I put 0 in for theta, this becomes the cosine of 0 again. And that, my friends, is equal to 1. So by your tangent line approximation, f of x is approximately, in this case, f of 0, or 0, plus f prime of 0, which is 1, times x minus, well, we're at 0. So, in the end, we end up with the following. And again, I shouldn't be using x in this example, because everything was relative to theta. So, give me a second. I messed that up. So this should really read f of theta, my friends. It'll be theta minus 0. Okay? So this becomes the following. It just becomes f of theta equals 1 theta when you're done with this. Okay? So as long as theta stays small, again, we're really close. Theta is not very big. It's pretty close to 0. We can say that for any value, sine of theta is approximately theta. Kids, that's pretty much going to complete the notes. There's a little bit of reading on the back that's relative to this, and I'll read it for you here quickly. But as I'm moving on to the next page, I want to tell you how much I've appreciated working with you guys in this class. I know the course is difficult, but keep plugging away. You're good kids. I appreciate you all so much. I know I won't see you in a couple days or whatever, but I'll be on a Google Meet with you. We're getting through to Wednesday. Just keep plugging away at stuff. I wish you all a Merry Christmas. And spend some time with home and family and stuff like that. That's what's important, all right? Get some rest over the break, and make sure that come back rested and ready to conquer the rest of the school year, okay? Seniors especially, it's gonna go fast. So that last example that we looked at, sine of theta equal to theta, this is actually somewhat important linear approximation. In optics, this linear approximation is often used to simplify formulas, okay? So this linear approximation is also used to help describe the motion of a pendulum and vibrations in a string. Not that you would need to know that, but if you're ever on Who Wants to Be a Millionaire, you wouldn't have to waste your phone call on it, okay? Kids, hope you have a great break. Love you all. Merry Christmas.